questions from the homeworks? Blake.
Could you do number 96, please?
Yeah, sure thing, Holmes. So 96 says, evaluate the logarithm or logarithmic expression to the nearest hundredth using your calculator and the change of base formula. So for doing 96, log base 12 of 259. So if I use the change of base formula, I can rewrite it. This as the quotient of 2 logs with any base. The base that I would choose if I'm using my calculator would either be base E, the natural log, or base 10, the common log. It doesn't matter. I always pick the natural log because it's one less letter to write. So I would just do in my calculator natural log 259 over natural log 12. So my answer there would be 224. Who's next? Maddie. 36. Copy. Bloop. Bloop. Okay, so you said you already were able to do part A just fine. Okay, for part B, all I'm doing is putting 600 in for P of T and solving. So I'm just going to do that on my calculator. And since that's going to be parentheses city, unless I use a that fraction command, I'm going to use that fraction command to avoid having to do a million parentheses, because like, who wants time for that? So that's in there. I'll go 0 to 100 on my x, because I don't really know what to expect there, but probably we're talking about a population of of deer. I would think 100 years is probably a long time for deer populations, because they don't live that long, right? Like 10, 15, 20 years. I don't know how long a deer lives. Probably not like 100. And then the y's, I know this is logistics, so the lower bound is going to be 0 and the upper bound is going to be the numerator. So in the interest of a round number, instead of doing 1,001, I'm just going to do 1,000. Whatever. There's my 600 line. Here's my logistic curve. I'm looking for the intersection. So second trace, intersect command, enter, enter, enter. So 24.5 years. And then the maximum is just the upper bound, so that's the numerator, 1,001. Okay. So no, there's no calculation to do on part C. It's just part of the, like a definition of how logistic works or whatever. Okay. Is that cool? All right. Yeah, no problem. Alex. 18, you say? Yes. Sure. So it says for 17 to 28, find the exponential function that satisfies the given equation. So this looks to be a population to me. So that's my population model. So P naught is the initial value. So 52. And then my R is 2.3. And since that's happening every year, I can just leave t in years and it can just be t. So I could simplify that down. So 1 plus 0.023 divided by 100 is just be 1.023. So that's good enough. Does that feel okay, Alex? Are you sure? I was kind of hesitant. Yeah. I just did 1 plus 2.3 divided by 100 on my calculator. I did it in my head, but like that's all I'm doing is just like evaluating that part to simplify it a little bit further. Okay. Raylan, you had a hand.
Yeah, can you do 33?
Sure. It says the number b of bacteria in a petri dish culture after t hours is given by the function b of t equals yada yada yada. When will the number of bacteria be 200? Use your answer to estimate the time it takes for bacteria to double. So I am solving this equation, right? I want to point out to you that if I multiply both sides by a over 100, you'd have this equation. Is that okay? Notice that this is answering the time it would take to double, which is actually the same, will be the same answer as that one. So the answer to both questions is going to be identical. I'm just pointing that out to save us a little bit of time instead of doing two separate things. Sydney? A over 100. So the hundreds cancel out and the 200 reduces down to 2 and you're left with A's. Where A is just any initial population. So 2 times A would be doubled, right? But since I did it to both sides, it's equivalent, right? All right, so let's do that. So 200, and then 100 e to the point, 693 t. Boom. Wow, that was a big one. Bacteria, do they live a long time or short time? Short time. Bacteria die real fast. Yeah, they don't live like years, a single bacterium. Like they reproduce really quickly and they die really quickly. So I think the amount of time that this is going to take to double, like 100 years or 100 hours is like kind of crazy talk. I'm probably guessing like 10 is probably sufficient. And then we're starting at 100 and going to 200. So I'll just use those as my 100 as my min. I'll do 300 as my max because, well, Mr. Kulik doesn't like the line to be at like the top of my viewing window. So there we go. That's good enough to find an intersection. Ooh, that was fast. Those frisky bacteria. Intersect command, enter, enter, enter. Basically, I get 1 hour. Those bacteria are getting busy. Now that's a joke because bacteria reproduce asexually, right? So that was a joke. Raylan, was that feel okay? All I'm doing is illustrating to you that the answer to the when will the number of bacteria be 200 is the same answer as estimating the time it takes for the bacteria to double. Notice that 200 is twice 100, so it's a doubling population. If I multiplied by like a over 100, where a could be any population, I'd end up with 2a equals a times e to the blah, 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 blah. So it's like literally double whatever that first population is. So we're just illustrating too that the initial population did not matter, that it's literally like for the population to double, any starting population is going to be the same amount of time, where it's going 100 to 200, or going from 1 to 2, right? Like that time it takes to double is going to be the same, regardless of how many organisms need to be created. The doubling time is the same. Does that feel okay?
Yeah.
Okay. Nat.
Can you please number
53. Jillian, did you have a separate question or follow up on that one?
It was a separate question.
Okay, you're next. So 53, it says, without your calculator to evaluate this expression, so the fourth root, we remember, is the same as the exponent, 1/4. Okay with that? And I know that log base e cancels out exponent base e. That was one of the properties we talked about. So it should just be 1/4. Or if you thought about it using the definition of a log, you'd say that e to the x is equal to the fourth root of e. And then it should be super obvious that x is 1/4. Same way. Is that cool? Okay. Jillian.
54.
Okay, same idea. So, because it's in the denominator, I know I can just use a negative exponent. So I'll just make it negative 1/7. Is that okay?
So then the entire answer is 1/7 or negative 1/7.
Yep.
Okay. So ln e is if they cancel out.
Yes.
So it's not like we're saying it's 1 to negative 1/7. The entire, like, how does the exponent become bad? I guess.
So if you think about, it's like this idea where we're just using the definition of a logarithm.
Oh, I understand. Okay, I see.
Does that?
Yeah.
So usually, conceptually, it's easier to just think about the two things just canceling out and disappearing.
Yeah.
But like really what's happening is that definition of a logarithm running in the background. Now it's more practical in most settings to just think about like, oh yeah, it cancels out and that leaves the exponent. Like practically, that's kind of how is the easiest way to understand it. But like really what's happening in the background is that definition. You know what I mean? Okay. Alex. Oh, sorry. Go ahead.
Oh, that's okay. I was going to ask you a separate one.
You can go. It's okay. It's fine. We're already on you.
97.
97. So yeah, it just to do the change of base formula, you can pick any base for the logarithm you want to use. So I would either pick, if we're using our calculator, either use log base e, the natural log, or log base 10, the common log. So I usually pick the natural log because it's one less letter to write. And then I just type that into my calculator. So that's it. No problem. Alex, you had one too, right?
Yes. Can we do number 42?
42? Sure thing, dude. Okay. So similar idea here. I'm going to think about 1 over the 5th root of 36. I'm going to think about that as 1 over the 5th root of 6 squared, right? And then that's going to be 1 over the 6th root of 2 to the 5th. Because I know that a radical is the same as a fractional exponent. The index of the radical becomes the denominator in the exponent. Yep. So what I can say then is log base 6 of 6 to the negative 2/5. Again, I made a negative exponent because it was in the denominator. Like so it makes a reciprocal. It's just going to be then negative 2/5. Because exponent base 6 and log base 6 cancel out. So the difficulty is just kind of rearranging the inner part so it has the same base as the exponent. And then you're just left with whatever the exponent is. Or same base as the log, I meant to say. Sydney?
So with 59,
With which one?
59,
Yep.
the answer would be 6.
Correct. Yep. And then the answer for 60 would be?
1/5.
Yes. And for 58, the answer would be 14. And for 57? 0.5. And for 56? 8. Good. And for 55? 3. You guys got it, right? That's good. Look at that. We just did like 6 problems in 10 seconds. Jillian?
Can you do 55? That's a lot.
3. We said it.
7. Yeah, can you?
So log base 7 and exponent base 7 cancel each other. And you're left with just the 3. If we rewrite that as a logarithmic equation, we'd say that like this is equal to x. So we'd say like log base 7 of x has to equal log base 7 of 3. So x is 3, obviously. Maddie?
Number 98.
98? I mean, it's like the same as 97 and 96.
Yeah, I don't know why. I can't like jump behind it for some reason.
Yeah, so
It's not working.
I can pick any log I want. I would pick the natural log. So I would just do natural log of 29, the argument, divided by natural log of 0.2, the base. And then I just type that into my calculator. And I'm done. NBD, right? Cool. All right, Alex.
So like when you do 61 for 62, is there ever what mode you put it in? Like if I like put it long time.
No.
It can be any mode.
Yeah. Yeah, degree or radian doesn't matter unless you're using sine or cosine.
Oh.
And then the function parametric polar only matters for graphing.
Oh, okay. Because I just want to make
So if you're not graphing and you're not using a sine or cosine, doesn't matter. Sound good?
yes.
Sure. And those are legitimate questions, all right? Like we've changed the mode a lot. Who knows what mode your calculator is currently in?
Yeah, I just.
It's worth double checking, like when does this matter and when doesn't it matter? I don't mind answering. Totally cool question. All right. We good with questions? Cool. All right. Let's we'll start 15.4 and then we'll go for a bit, and by 10:15, if we haven't stopped by then, somebody stop me so we can do the homework quiz, okay?
Is it a partner quiz?
This one was going to be individual. feels like, anyways. All right. So, in section 15.4, we're going to finally get to solving these exponential and logarithmic equations. So at this point, we've been dancing around solving these exponential equations by like doing it by graphing. Right? We've graphed things and found the intersection. We're going to actually get into doing this algebraically. So the foundational idea of what we're going to be doing is using kind of this one-to-one property. We're going to say that if we have two exponentials that have equal bases and are equal to each other, then the exponents have to be equal. Which intuitively is like super common sense, right? Like if 2 to the third equals 2 to the x has to be 3, right? Like, no dir. Right, Mr. Kulik? No dir. And we can say the same thing with regard to logarithms. Everybody's okay with that idea? Okay. All right, so let's now burn through some examples. So we have 12 times 3 over 2 to the x over 5 equals 27. This is a solving problem, right? So instinct would tell us the first thing we should do is what? Okay, getting x by the self is the goal. What's the first step into doing that? Can I multiply the 12 to the 3 over 2? No. Why can't I do that?
You have to work with the exponent first.
The exponents are different. If it was also 12 to the x over 5, then yes, we could multiply them together. But since the exponents are different and the bases are different, we can't multiply them together directly. Okay? Everybody's cool with that? What can we do? Oh, guys. Divide by 12. Yeah, exactly. Let's get that exponent base by itself. And 27 divided by 12 is 9 over 4. So right now we have a b to the x. Everybody agree with that? That's like some base with an exponent on it. Everybody agree? I want to now find a way to rewrite 9 over 4 as 3 over 2 to some power. Maddie? Great. So 9 over 4 is 3 over 2 squared. And then if we use our one-to-one property, we can set the exponents equal to each other. And we multiply both sides by 5 to get x equals 10. Is that okay? Now, alternatively, or equivalently, I should say, let's say we're here, and sometimes it's really difficult to find a way to rewrite the two sides so they have the same exponent base, right? Sometimes that's not trivial and it's rather difficult to do, or maybe it's kind of feels like it's impossible to do. It's never impossible. Well, I mean, if the number was equal to a negative or something, it would be impossible, or 0. Because we know an exponential can't give us a negative number or a 0. But, okay, so what could we do in this case if we had difficulty determining that 3 over 2 is the same, or 3 over 2 squared is the same thing as 9 over 4? Sydney? I'm going to use a logarithm to cancel the exponent base on the left-hand side. Log of what base will cancel exponent base of 3 over 2? Sydney? 3 over 2. So I can do log base 3 over 2 to both sides. Those cancel out. And we can multiply both sides by 5. And then it's just calculator time. Remember, to get log of any base, you press the math button and then scroll down and find the log base command. And we get the same 10 that we did doing it the other way. So either method is appropriate. Is everybody okay? Is this looking familiar? We did do this last year. You could answer when I ask those hypothetical questions like, does things look familiar? And it's okay to give me like the answer I'm not hoping you're gonna say. Like you could be like, nah man, like
I don't even know what a log is. There you go. Since you don't want to know.
I know, right? It's the answer to an exponential equation. Right? Like log base b of c is, you know, the power of b that gives us c. It's the name for an exponent or an answer to an exponential equation, you know? How's that?
It's fabulous.
You know? I gave you the really terrible explanation.
Oh, really?
You don't want it. It's like a 20-minute explanation.
I don't really want that.
Okay. I didn't think you probably did. Because the explanation I gave you is adequate now, but becomes inadequate eventually. But like, yeah, we'll worry about that when it eventually rolls around. Like in like 4 years if you're still taking math classes. All right. Next example. First thing you want to do is divide by 14. Very good. Okay. So one way we could do this is try to rewrite 9 as an exponent of, or as a exponential with base of 1/3. Anybody see it? It's -2. 9 is 3 squared. And to make a reciprocal without changing it, I have to make the reciprocal and give the exponent negative. Now that's a little bit harder to see than the previous one was. What would we do alternatively? I could do log base 1/3. Of both sides. And if I go to my calculator, I get same -1.
The notes are just completely wrong. It says -3. It's everything the exact same. It just says -3.
Oh yeah, that's weird.
Wrong.
Yeah, that ain't right. Well, good thing we're doing it together, right? Of course. All right. Let's do another. This one, quite a bit trickier. There's probably 3 things that you see right away that are like, that's a lot more complicated, or makes this more complicated. What are the 3 things that we see that making this more complicated? We have x in 2 different places, yes. We have a fraction and negative exponent.
We don't like negative exponents.
Yeah.
First thing you gotta do though is you gotta multiply out 4.
Yeah, I agree. So Blake says multiply both sides by 4 to start. Let's take care of that fraction piece. Okay. Everybody cool there? Can I add 3 to the x and 3 to the negative x? No. Those are unlike terms. Why are they unlike? They're not identical, right? The exponent is different. Okay? Well, let's try to get rid of the negative exponent part. How can I do that?
I mean, you could just make it 1/3 of the x.
We could make it 1/3 of the x, but that's going to give us a fraction again.
I like fractions.
And we'd prefer not to get a fraction. Here's the trick. I multiply both sides by 3 to the x. So that's going to distribute through. So what do I get when I multiply 3 to the x times 3 to the x?
3
3 to the 2x. X plus x, right? What do I get when I multiply 3 to the x by 3 to the negative x? 3 to the 0, which is just 1.
Yeah.
I am now going to get everything onto one side. Now, this equation that I've written has 3 terms on it. What other kind of equation that we've solved has 3 terms like that commonly? A quadratic, a degree 2 polynomial. Would you believe me that this is actually in the quadratic form? It is. So recall that the exponent of an exponent property is this. You guys remember that? So I can rewrite 3 to the 2x as 3 to the x squared. Definitely looks pretty quadratic now. And just to hammer this home, let's do this silly substitution so that everybody's completely convinced we have something in the quadratic form. Everybody cool? Heck yeah. How do I solve a quadratic? Use math, that's true. There's 2 methods that we would commonly use: factoring and quadratic formula. Since this has a leading coefficient of 1, let's check the factoring first, because if it factors, it should be really easy to do that. Multiplies to give us 1, adds to give us -8. You know 2 integers that do that? There aren't 2. So what should I do instead? Quadratic formula. Who remembers the quadratic formula?
X equals -b plus or minus the square root of quantity b squared minus 4ac.
Okay.
Oh, and with 2a. I don't know, there was like a little, you know, like Mr. McCaskey's jingle.
Oh my goodness. What did I do here?
For you, I will.
There we go. So what do I get here? I get 8 plus or minus the square root 60 divided by 2. 60 is the same thing as 4 times 15, right? Why is that a helpful observation? Because the square root of 60 then is going to be the square root of 4, which is 2, times the square root of 15. So those can reduce down to that. Are we done? No, why not? Nope. What are we supposed to be, which variable are we supposed to be solving for? X. What have we solved for?
Y.
Y. What is y equal to, though? 3 to the x. What? Oh, thank you. On the 15. When I said first equation, I was looking up at the quadratic formula. Like, it's right there on the quadratic formula. It's not your fault. I made the mistake. It was just confused at the way we phrased it. That's okay. We got it, though. Glad you're paying attention. Okay. So how do I solve for x? Yes. Which log do I use?
3.
Log base 3. Very good. And I'll go to my calculator. Now, it's worth pointing out here that sometimes I can get an error when I type this thing into my calculator. I won't in this case. Why would I be getting an error sometimes? Because what?
Oh, you can't, can you not have like a negative?
Yeah, you cannot take the logarithm of a negative, well, let's say a non-positive number. So 0 or a negative is going to be a problem. So not every one of these equations like this could have two solutions, right? Maybe one of them is positive, the other is negative, in which case you get just one answer. Or maybe, both of these answers could be negative, in which case you get no solution out of that. That's okay. Is everybody okay with what I did there? That one's a little sneakier, right? Okay. Let's go and look at some logarithmic ones now. Okay, what do you want to do first here? Divide by 3? Yeah. Okay, then what? Is it practical to try to rewrite 2 as a log base 10 number? Yeah, it's kind of yucky. Let's not. Instead, let's just convert this to the exponential form. So I can say b to the solution is equal to the argument of the logarithm. Oh, what's x? Yeah. Now, hold on. Let's be careful here.
Plus or minus 10.
Mm-hmm. Why the plus or minus?
Square roots.
Okay. Now, we're not done. Because on all logarithmic equations, we can get an extraneous solution. So we do have to check these answers to make sure they actually satisfy the original equation. The check, though, is very easy. All we need to do is make sure that when we plug our values in for x, the number inside the logarithm is positive. So 10 squared, positive. That one's good. Negative 10 squared is positive. That one's good. They both work.
Okay, so it can sometimes be one or the other, or both.
Yes, or none.
Yeah.
All possible.
Yeah.
All right. This will be our last example today, and then we'll do that homework quiz next. Sound good to you guys? All right. What do you want to do first here? This one, again, looks considerably more complicated than the previous one. What's complicated about this? What's more complicated about this? We have 3 different natural logs. That's a problem. And what else is different? We have 3 different x's. We have x's in 3 different locations. Ew, boys, yeah. What should we do? Add them? No, but the sum of 2 logs is the product property, so I can condense the logarithms on the left-hand side. Absolutely. Everybody's okay there? Similarly, on the right-hand side, what can I do?
Oh, it would be, I think that's the natural log of x squared.
I can use the power property to rewrite that as the natural log of x squared.
Numbers, x squared, x squared.
You said it right.
Oh, I said x squared.
Yeah, you said it right.
Cool.
Is everybody happy with what I did there? Now, notice that I have the natural log of stuff equal to the natural log of some other stuff. What can I do? I can just drop the natural logs, right? By using this same one-to-one property up from here. Right? The log of x is equal to log of y means x is equal to y. While I'm at it, I'm going to FOIL this thing out for you guys. Huh? What does this look like? Quadratic equation. What do I have to do to solve a quadratic equation? I have to do something first.
Oh, you have to equal the x squared.
Make it 0.
Yeah, it has to equal 0. So subtract x squared from both sides. To solve a quadratic, we can either
Factor or use a quadratic formula.
factor, use the quadratic formula. Since leading coefficient here is not 1, if I am able to factor it, it's going to be that long factor by grouping thing. And I'm not even guaranteed that that'll work. I would just use the quadratic formula here without even thinking about it. This one does factor. I agree, it does. But it's like not significantly less work than to just use the quadratic formula. So that's usually my default. So I have 25 minus 16. So that's 9. Square root of 9 is 3. So 5 plus 3 over 4 is 2. And 5 minus 3 over 4 is 1/2. Am I done though?
No.
What do I still have to do?
Check.
Check them. So if I take the 2 and I plug in here, 3 times 2 minus 2, positive. 2 minus 1, positive. 2, positive. That one works. If I do the 1/2, I plug into the first one, not positive. My pen, oh, there it goes. Not positive. So this is, what do we call that? Extraneous. That was the word I was thinking. So I have just one solution here, 2. Does it matter that 1/2 would be positive in possibly some of the other logs?
No.
No. As soon as you find one place where it's negative or 0, you're done. It's extraneous. And to be super clear, when you're checking, you must check at the very beginning original equation before you've done any condensing or anything else, right? The checking has to be at the original problem, not some intermediate step along the way. Okay? At this point, you guys can do 99 to 100. That's going to go into part of next week's problem set.
Whoa.
99 to 130, sorry.
So 99. So
It's
okay.
It's right here.
Okay.
It's right here.
Like is done.
Dang, man.
That's
So,
where we're at.
so how do you find them, like, if you have like a more complex,
If you have a complex number,
like instead of like 1 or like 1.4,
Oh, you plug in all the
like how do you like, you can't really condense that down, like,
1.4.
yeah, like let's just say you have a question, okay, hypothetically,
Okay.
that is 1.06 to the x power is equal to 4.1.
And then you have to work for in order for it to be considered.
That's it? Perfect. Okay, thank you.
Yeah.
That's what I thought it was.
Yeah.
Okay.
So, all right.